Let us turn our perspective to a very common type of data sets found in application, namely time-oriented data. I'm going to divide the discussion of time series analysis into two parts. With this lecture, I'll introduce you to some very basic concepts, a couple common processes, and some all-purpose tools for modeling. In the next lecture, I will devote the use of regression towards modeling time series data sets. Let me motivate our journey with an example related to an offer given by the snowblower manufacturer Toro. The offer was called Snow Risk, and it was stated that if you buy a Toro snowblower, and if the snowfall for the season turns out to be less than 10% of the historic average of the area where you reside, then you will get all your money back and get to keep the snowblower for free. If the snowfall is less than 50% of the historic average, then you get 10% of your money back. It sounds like a great deal, or is it? Here is the hint. I'm guessing most customers will naively read this deal as if one gets a 100% refund if the snowfall is in the lower 10% of the snow distribution. Thus, a naive customer will figure that there's a 10% chance of getting a full refund and a 50% chance of getting a 10% refund. The trap is made more possible when one looks at the red circles on the ad. Notice that the white snow in the left circle, which you can see here, is less than 10% of the full red circle, and the white snow of the right circle is slightly less than half of the full red circle. These visuals in the ad turn out to be very deceptive. Here is a screenshot from Home Depot for a Toro snowblower with a selling price of $7.99. Home Depot on its webpage advertised the snow risk offer as opposed to a sales price. An interesting question is how much of a straight up sale would make us indifferent between the snow risk deal and the straight up sale with no conditions. To assess the deal, we turn to data. The Toro deal was offered in the fall of 2013 before the snow season. A first step would naturally be to use data to make a prediction of snowfall for the winter of 2013. We will get past year's snowfall totals and analyze the time series. When analyzing a time series, we need to determine if the series has a pattern or if the series is random. We will lean on two basic data checks. One, a time series plot, and two, an autocorrelation function, or ACF for short. Lots of environmental data are publicly available. Here's a site where I found annual snowfall totals for Milwaukee. Here are more than a century's worth of snowfall totals in JUMP. What I want to do now is create a time series graph. There's a couple ways of doing that in JUMP. One way is to create a time index, which I'm going to call T, and I do that by right-clicking, new column, and then giving a name of T, as you see here, and then below where it says initialize data, choosing sequence data, and that will automatically put an index that goes from 1 to 2 to 3 and so on. I then went to Graph Builder and dropped the total on the vertical and dropped the T index on the horizontal. I clicked the line connection button on the top, and that would connect the points. I also double clicked on the vertical axis and put a reference line at the mean. This is a time series graph of 100 plus years of snow totals in Milwaukee. Looking at this time series graph, we don't really see any patterns. it basically looks like coin flips around the horizontal mean value. We don't see trending. We don't see cyclical movements. Let's confirm that with a more sophisticated test. Before we get to the alternative test of randomness in a time series, let's show you another way to get a time series plot. You can go to Analyze, Specialized Modeling, Time Series, give the Y variable that you're plotting, in this case total, and you'll automatically get the time series plot you see on this slide. Let's investigate deeper the question of randomness. When dealing with time series, we often consider how observations relate to previous observations. This is the concept of a lag. I'm going to lag the data here, and the way I'm going to do it is highlight the total column, use the option of New Formula Column, then go to the row group, and then choose lag multiple. In lag multiple, as you can see here to the right, I'm picking the lags from 1 to the last lag of 2. You'll see what this produces. What gets created are two lag variables, which I have called total-1 and total-2. Let's, for example, look at 1887. Snow total in that year was 77.1. If you go up, it's 110.3 in the previous year, and then prior to that, it's 32. But we see those values on the same row of 1887, 110.3 here and 32. So we're lining up the previous year and 2 years in a given row so that we can compare them. We can look at things visually. I have here two scatter plots of snow total in any given year versus what the snow total was the previous year and what it was 2 years back. We can equally look 3 years back and 4 years back, but this is just to give you an idea of the comparisons of lags. And we see that there's really nothing going on here. These look to be random scatters if you look 1 year back and you look 2 years back. Now we can calculate a correlation between snow total and 1 year back and see if that correlation is significant. We can calculate the correlation between snow total and 2 years back and see if that correlation is significant, and so on. There's an easier way, as we'll see in a moment. I showed you a few slides back that you can go from Analyze to Specialized Modeling to Time Series to get a time series graph that you see here on the slide. Also, what comes with it is an autocorrelation function, or ACF for short. ACF is basically showing you the correlations between snow totals and lag snow totals. Also, it's giving you a bar graph of those correlations. The ACF starts with lag 0, which we can skip over because the correlation between snow total and itself is obviously 1. Below, we find the correlations for lag 1, lag 2, lag 3, and so on. These are referred to as autocorrelations. And we see also a graph of these correlation values that are given on the left edge. Furthermore, what JMP provides are these bandwidths, these limits that can be interpreted as the following. If the process is random, then we would expect 95% of the time the correlations to fall in between the lower and upper limits. We see here that these correlations are basically swimming within these limits, indicating no evidence that the underlying process is not random. As such, our conclusion is the snow total process is following a random process. Now, JMP provides these sophisticated tests on the side here. Let's just not worry about it. We'll just look at the ACF, the bar graph, and draw our conclusions from that. We have now concluded that the snow totals are random over time. We can now turn our attention to ask the following question. What is the distribution of this random variation? I'm showing here a histogram and normal quantile plot of the snow totals. And we see that the distribution is slightly positive skewed. We have a couple options. One, we can transform the data. For example, take the data to some power or log the data to make the data more normal and then analyze from there. Or we can fit the original data to a non-normal distribution. I'm going to do the second one just to show you some neat capabilities in JMP. With the red arrow option, I choose continuous fit and then fit all. What JMP will do is consider various distributions and see which of those distributions best fit the data. It's going to sort the choices and ultimately rank the choices based on AIC. Remember, smallest AIC is better. And interestingly, you're learning here that AIC is not just used in a regression context, it is used in general for helping the analyst find best fits for the data, in this case, best distribution fits. What JMP reports is that the gamma distribution is the best fit. Actually, if you go down here, you find the normal distribution is several distributions down the list. So we'll go with the gamma distribution, which is plotted on this histogram and really form fits very nicely to the histogram. And the estimates of the parameters of the gamma distribution are given here. Now, I'm not going to have you worry about learning the gamma distribution. We just see that it has found an alternative distribution than the normal to better fit the histogram. Now with the gamma distribution, I'm going to go to its red arrow pull down, choose process capability. What this will allow me to do is calculate probabilities under the gamma. I see here the option of entering spec limits. Now that's like for manufacturing kind of talk, but we can apply it here to the snow total. And notice I put on the left box, which is called LSL, lower specification limit, the number of 4.77. What is that? Well, the average snow total for Milwaukee over the 100 plus years is 47.7 inches. I'm taking 10% of that, which is 4.77, and asking JMP to tell me what is the estimated probability that snow total will be less than 4.77. Let me remind you why we're calculating this probability. The Toro deal states that we will get the snowblower for free if the snow total is less than 10% of the historic average. In Milwaukee, that would mean if the snow total is less than 4.77 inches. From the gamma fit, we find that the expected percentage to the left of 4.77 is 0.0019. This number is in percentage terms, so to convert it to probability, we move over the decimal place by 2 places to get the following estimated probability. The probability that X is less than 4.77 inches is equal to 0.000019. That says the probability of snowfall being less than 10% of the historic average is estimated to happen less than 2 times per 100,000 years. Boy, that's a really generous offer. What about the probability of getting a 10% discount? Remember, that would be if the snow total is less than 50% of the historic average. We find that probability to be 0.0741. It does happen, but it's not a very likely scenario. This slide summarizes the estimated probabilities we have found. So the probability of 100% savings is 0.000019. The probability of a 10% savings is if snowfall falls between 4.77 and 23.86, which we find here to be 0.074081. And we can talk about the expected savings to the customer. We can basically get a weighted average. 100 will be realized with the probability that we can see right next to it. That's the weight. Plus 10 can be realized with the weight that we can see right here. Plus getting no savings with the remaining probability. This translates into an expected savings of 0.7421%, which is less than 1%. Translating the 0.74271% savings to dollars for a $7.99 snowblower would be $5.93 expected savings. Let me repeat this. $5.93. Toro's offer is no better than offering the customer a Frappuccino from Starbucks to purchase their snowblower at full price. This is a totally bogus offer from the customer's perspective, but my guess is that many customers will fall for it. So Toro will win out on the naivete of statistical thinking of the consumer base. And I should say that there's no doubt that Toro is protecting itself with a backdoor insurance policy in case the most unlikely scenario were to occur. In terms of the snowfall that actually occurred in 2013, 45 inches. None of the customers got the snowblower for free. None of the customers got that 10% discount. This snow series gave us a nice example of experiencing a time series process. And this snow series had a few features to it. Feature 1, the general overall level of the series stayed constant over time, over that 100+ year span. Feature 2, the level of variation of the data appears to be about the same throughout the series. If you go back and look at the time series plot, the data are not funneling. The variation above and below is pretty much constant over time. And in feature 3, there is no persistent pattern in the sequence of consecutive observations. That means that the snow amount of any given year is not predictive or providing insight for future years. Features 1 and 2, the level being constant and the variation being constant, define what we call in time series jargon a stationary process. If the process is additionally patternless, that would be feature 3, then the series is called a random process. Let's summarize a random process with an expression, an equation. We have here yt, where t is the time index, equals some underlying mean plus random variation. These are random errors, or we call them white noise. On average, they're 0, and they have constant variance. And the distribution of these random errors we assume to stay the same over time. When we have this situation here, we'll see a process that on average over the long run will indeed be at the mean constant value of mu. In technical jargon, we say this process y is independent and identically distributed, or IID. Independent means the observations are random over time. Identically distributed means that the variance stays the same and the nature of the distribution stays the same. For example, they will remain normally distributed over time. Clearly, with this simple random process, the fitted model would be y bar. That would be our estimate for mu. Thus, the forecast of future periods is simply y bar. I'm denoting the forecast as y hat sub t plus L, where L is 1, 2, 3, 4, and so on. For example, when we have y hat sub t plus 1, that would be the forecast of one period in the future. For a random process, our best guess is just projecting y bar into the future, however many periods into the future. Now let's talk about non-random processes. They can come in a variety of ways. Here are some simple examples. Up here we have a linear uptrend. That's clearly non-random because the future is not guessed by simply taking y bar. We have a linear downtrend. Here we have a process that I'm calling stationary meandering. Meandering in the sense, like a river, it's moving around up and down, but it's stationary because it's basically staying put around some average level. Whereas non-stationary meandering, we have these ups and downs, but there seems to be a tendency for it to run away. Here are some more examples. Oscillation, up, down, up, down, up, down. This is not random because consider the end of the series that is down. Your best guess for the next one is not y bar, but up. There is a distinct pattern here. Here is a process which I call non-constant variance. Though the ups and downs may be random, the variance is not constant. It's funneling, it's getting greater. So we do not have an IID process. Here we have seasonality. These are data on the 7 days of the week. We're actually going to later analyze this data, but we can clearly see the 6 and 7 are the weekends are showing seasonal patterns from week to week. Now, we could have combinations of any of these situations. We could have, for example, a series that's trending and seasonal. So this is just giving you a sense of what non-randomness could be. Now that we've talked about a random process, let's talk about another unique process called a random walk. And it's a process that you should be familiar with because it does describe certain types of series that are in business applications. You'll see what I mean in a moment. A random walk describes the motion of things. Back in 1905, a famous statistician named Carl Pearson coined the term to describe the movement of mosquitoes over time. Albert Einstein modeled the path of dust particles in the air that collide with gas molecules with a random walk. And in 1900, a doctoral thesis called The Theory of Speculation by Louis Bachelier set forth this revolutionary conclusion that, quote, there is no useful information contained in historical price movements of securities. Now, his conclusion stayed untouched for 60 years until Nobel Prize economist Eugene Fama of the University of Chicago and others expanded on his finding to develop the revolutionary random walk theory, which asserts that stock prices continually react to new information and their movements are random and unpredictable. Here's actually a famous book called A Random Walk Down Wall Street, written by a Princeton economist who later became the dean of the Yale School of Management and then became chief investment officer at an investment firm. And I'll have you read here this excerpt from his book. Basically, it says in the end, we'd be foolish to believe that we can predict the movements in the market because they're just random. And you can do no better than just literally flipping a coin. which is the gist of what he states there. I'll have you read that excerpt. Let us write down the random walk model. I'm going to consider prices, so I'll use PT as you see here. In particular, the price at time t equals some underlying constant, mu, plus the price at time t minus 1 plus random error. If we bring the previous period's price to the other side of the equal sign, we have the change in prices, which I'll call dt, which refers to the difference in prices, equals mu plus random error. Now what do we have here? We're saying that the change in prices is equal to mean plus random error, means that the changes are following a purely random process with some mean mu. When mu equals 0, we have what's called a random walk with no drift. When mu is not equal to 0, we have a random walk with drift. To get an idea of how random walks behave, let me run a simulation. I'm going to take a random walk with no drift and simulate some series. In particular, I'll look at price at time t equaling the previous period's price plus a random error. Now remember, the random error could be positive or negative, but on average, they're 0. We'll start out the simulation at 0 and let this equation here dictate the processes. What we get from the simulation is seemingly 3 fundamentally different series. The top one seems to suggest to us a trending up series. The bottom one seems to suggest to us a trending down series. The middle one staying put. However, these are false conclusions. None of these series have an underlying drift, an underlying propensity to go one direction or the other. In fact, at the endpoints of any one of these 3 series, they could go up, down the middle, or down. What these series do have in common is the meandering type movement that we see with each and every one. So when we see meandering, we might think about a random walk. We'll also see other types of meandering behaviors that will not be modeled by a random walk. Let's now look at real data. Here we have a time series plot of Honda weekly closing prices from January 2015 to July 2020. We see the distinct meandering, so let's consider the possibility that this follows a random walk. Let's take a look at the ACF. Notice the significant correlations that lag 1, 2, 3, 4, and so on. This suggests we have a non-random process, and let me emphasize this point. A random walk is not a random process. It is a non-random process which has a unique characteristic to it, namely the differences between successive observations is a random process. In a previous lecture, I showed you how to take the differences between successive observations. In particular, for this application, what we'll want to do is highlight the price column, then go to new formula column, then row, then difference. And we see here a time series plot of the changes in weekly Honda closing prices. What do we see? We see a random series where the changes go up and down, but they look like coin flips. There's no pattern to this series. This goes hand in hand with the random walk model that says changes in prices will behave randomly. Here is an ACF of the Honda price change series. We notice that all the autocorrelations are falling within the 95% significance limits, unlike the case earlier on the original prices. We have indeed confirmation here of a random process. It's safe thus to conclude that the differences in Honda prices, PT minus 1, is following a random process, some underlying mean mu plus random errors over time. The question is if the random walk at hand has drift or not. The implication would be on the mu value that underlies this process. We want to test whether mu equals 0 versus mu doesn't equal 0. That simply can be done with the test mean option in JUMP, which I showed you back in the inference lecture. I'm going to give those differences and test specifically the value of 0, as you can see here. We can look at the two-sided p-test, which is 0.9535. Since that p-value is large and greater than 0.05, we do not reject the null hypothesis of mu equaling 0. Thus, there is no evidence of drift to this price series, and we would conclude that we're dealing with a random walk with no drift. Now that we have found that the Honda price series follows a random walk with no drift, how do we make forecasts? Well, we have the random walk with no drift up here. Price at time t equals price at time t minus 1 plus the error at time t. We can push the subscript into the future and talk about the price at time t plus 1, which would equal the price at time t plus the random error at time t plus 1. Since this is a future random error, and since on average random errors equal 0, we will simply put a 0 value here for the random error. We don't know if it's going to go up or down. We'll take the unbiased replacement of 0. This means the prediction of price at time t plus 1, that's why I put a hat on top of p, simply equals this period's price. Here we see this Honda series ended at 25.309999, which is basically 25.31 at period 292. This would mean the prediction of period 293 would be the price at time 292, which would be this value of 25.31. When we use the current observed value as the prediction for the next period, this is referred to in time series as a naive forecast. Let us turn to another example. Let's look at Apple weekly closing prices over the period of January 2010 to July 2020. Now we can clearly see the meandering behavior again. This one is going up. Is that suggestive of a random walk with drift, or is this a random walk without drift, implying that it could equally start going down? Let's investigate that question. The first thing I did was take the changes in prices, and we see here a series that is flat lined. However, the variability in this series is increasing over time. So we don't have an IID process. We have a process that may be patternless, but with increasing variability. What's going on here? Well, if you look at the previous slide, you'll see that Apple prices have increased greatly over that time. And it may be that the changes in prices are constant in terms of a percentage, but a percentage of a higher Apple price will be a greater swing. So let's change our units to percentage changes. What I have done was take the natural log of the apple prices and then take the differences. And this gives us percentage changes in weekly apple prices. Or, as I've used the term in a previous lecture, the weekly returns. Notice that the weekly returns of apple prices is a random series and a series with constant variance. We see that the prices from one week to the next could change as high as 10% or as much as you can see down here, minus 15%. So basically most of it's falling within plus or minus 10%. Let's look at an ACF of the changes in natural log prices. We see the ACF is consistent with a random series, as we saw from the previous slide with the time series plot. Remember again, we're looking at the changes in logged prices, and we're going to ask a similar question. Are these changes having an underlying mean mu different than 0, suggesting a random walk with drift? Here we find the average changes in log prices has a value of 0.0050588. Now, remember the changes are returns, so this would be the estimated average weekly return. It's the estimate of mu. The question is that value significantly different than 0? I'm testing, as you can see here, with the test mean output against 0, and we find the two-sided p-value to be 0.0013, which is small, and we would reject the null hypothesis of mu equaling 0, which suggests the log prices follow a random walk with drift. Let's now forecast the apple price series. We found for the apple price series that the log of price at time t equals some underlying mean plus log of price at time t minus 1 plus random error at time t. Pushing the subscript into the future, we would have the log of price at time t plus 1 equaling mu plus log of price at time t plus the future random error, which we can assume to be 0, giving us the forecast of the log of price at time t plus 1 equaling r bar, which is our estimate for mu, the average weekly return, plus log of price at time t. The series ended on period 553, so we are talking about forecasting period 554. The log prediction of price at time 554 would equal the average return, which we saw from the previous slide, plus log of the last price. We can see that right over here, 425.04. We get a prediction in log units of 6.057242. To get back to original units and our prediction of price for period 554, we would E that value to come up with our prediction of 427.196. I kind of would call this forecast a naive adjusted forecast. It's not a straight up naive forecast in that it's using the last observation as a prediction for the next period. It's using the last observation plus an adjustment, as you can see here, with the estimated drift component. Our basic goal is to model the time series at hand. In this lecture, we have learned that for a random process, the appropriate forecasting model is simply y bar. For a random walk process, we learned the appropriate forecasting model is either a naive forecast or a naive forecast adjusted by the average price difference or by the average return. What about other behaviors? There are a few approaches one can take. One approach would be to use a smoothing method, examples being the moving average method or the exponential smoothing method. Another approach is to use regression. And finally, we could talk about sophisticated time series methods such as ARIMA. I'm going to finish out this lecture talking about basic smoothing methods. Next lecture, we will focus primarily on regression. I'll make quick note of ARIMA. Smoothing methods are used for one of two purposes. One, simply to wash out the noise to see the long-term movements of a series and not necessarily do explicit forecasting. Another is indeed to implement them for forecasting. I'm only going to cover the most basic smoothing methods, the first being the moving average. The moving average is simply, at time t, the average of the k most recent observations, k being the span of the moving average. You can use these moving averages by themselves to show the movements of the time series in a clear picture, as I'll show you in a second. You can also use these moving averages as forecasts. Here I have the forecast for t plus 1 as the moving average value computed at time t. During the pandemic, we saw actually moving average plots all the time. Here are a couple examples, and you can see that I boxed off that they are on the number of cases and deaths, 7-day moving averages. This is smoothing out the jumpiness in the daily data over the course of a week. And we can see the moving averages here in the solid blue line and in the solid black line are easy to follow relative to the jumpy, highly variable individual observations. Smoothing out time series with moving averages is common in financial sectors. Here we see the Dow Jones with its variability, but you also see the smooth lines of moving averages. I've computed a couple different moving averages, one with a span of 50, the other with a span of 100. Clearly the 100 will be even further smoothed out than the 50. Here we have the daily trading volumes of Netflix stock, and I'm going to compute the moving average with span 2 and the moving average with span 3. The above screenshot shows the moving average based on span of 2. You can see the forecast for the third period that I've boxed here is the average of cells B2 and B3. So these two are averaged and they project into the future as a forecast. Then we can copy this down so that the next two will be averaged to be the forecast of the future period and so on. For a moving average 3, I'm taking the first 3 periods and averaging those to be the forecast for period 4, and then continuing that theme down the column. Now that we have the forecasts, we can plot these forecasts along with the original series. So I have highlighted the first 3 columns, which include the date, the original volumes, and the forecasts of those volumes based on a moving average 2. I went to insert and then a line graph. Here you can see the forecast superimposed on the original volumes, and the moving average doesn't do a bad job. It seems to be tracking along pretty well the ups and downs of the series. Beyond visually assessing how well a forecasting method is doing, we need some formal measures. For basic smoothing methods, there are three common measures of forecasting accuracy: mean square error, mean absolute deviation, and mean absolute percentage error. Mean square error, or MSE, is the same notation we've seen in a regression setting, but in this setting it would be getting the average of the squared prediction errors, where M here denotes the number of periods for which we are assessing the performance of the time series method. Mean absolute deviation, or MAD, is the average of the absolute values of these prediction errors. Mean absolute percentage error would be taking each prediction error in absolute value, dividing by the observed value. So this would be giving us basically a percentage of how off it is relative to the baseline of the actual value of the observation. Getting the average of these, multiplying times 100 to turn it into percentages. Here's a snapshot of some performance measure calculations. Let's look at row 5, for example. The observed volume for this row is 7,033,200. The prediction based on a moving average span 2 is 7,310,500. If we take the difference, we get the prediction error, and we can take the absolute value to find it to be 277,300. Though I don't show it here, if you were to average down this column E, you would get MAD for the moving average too. Instead, what I did was I took the prediction error in absolute value and divided it by the observed value of 7,033,200, multiplied times 100 to give the prediction error in terms of how off it was in percentage terms. Averaging down this column, we get mean absolute percentage error, which we find for the moving average 2 to be 31.068%. You can also see I calculated MAPE for the moving average 3. Smoothing methods work on the basis of giving the greatest weight to the most recent observations. Consider a moving average 3. By dividing the sum by 3, we're giving weights of 1/3, 1/3, 1/3 to the 3 most recent observations, but thereafter the weights are 0, as you can see here at the bottom. This is an all or nothing proposition and a major step down in the weights. It might be preferable to have the weights steadily decline as we go from the most recent observation and going back in time. Let's talk about that. One way to have weights progressively decrease moving back in time is through the simple exponential smoothing model. It's given by the forecast of time t plus 1 equals alpha times the observed value at time t, which is yt, plus 1 minus alpha times the forecast of time t. Alpha is known as the smoothing constant, and it's traditionally between 0 and 1. However, that's not necessarily required. And 1 minus alpha is known as the dampening factor. If you unfold this equation, you'll find that the weights moving back in time are alpha, and then alpha times 1 minus alpha, and then alpha times 1 minus alpha squared, and so on. So, for example, if alpha equals 0.6, the weights will progressively and exponentially decrease as 0.6, and then one back would be 0.24, and then 0.096, and so on. Well, this exponential smoothing method has to start somewhere. If we go to the very beginning, we will find in particular the forecast for period 2 will equal alpha times the observation at period 1 plus 1 minus alpha times the forecast of period 1. But there's no period prior to period 1. we have to initiate this y hat 1 with a value. The traditional initiation is to set it as the first observation. Some packages will do some other fancy initializations, but in the end, it really doesn't matter because when we go far enough into the future, the impact of that initial forecast is totally dampened out. Consider a monthly time series with the variable PMI. PMI stands for Purchasing Managers Index, and it's a common measure used by economists to reflect the health of the U.S. economy. I'm going to implement an exponential smoothing method with alpha equaling 0.7. The first observation is 57.2, so that will serve as the forecast for period 1. Column C will have the forecast. The forecast for period 2 will equal 0.7 times the observed value in period 1 plus 1 minus 0.7 times the forecast of period 1. Both of these values here in the equation are 57.2, so in the end you'll get 57.2 again. This will always happen when you initiate the first forecast as the first observation. The next forecast will also be the same value. Things will break up with the next forecast thereafter. In particular, the forecast of period 3 made in period 2 is 0.7 times the observed value in period 2 plus 1 minus 0.7 times the forecast of period 2. The observed value in period 2 is over here, 55.8. The forecast of period 2 is above here, 57.2. In the end, you get 56.22. You can see that value there. You can put the formula and embed it in the cell right at the top here of C3. In C2, I typed in 57.2, but then I embedded the formula and then just copied it down to get at the bottom the forecast for period 101 to be 57.9885. Here you can see the superimposing of the forecasts on the original series, and the forecasts seem to be tracking the original series quite well. Granted, the alpha of 0.7 tracked the series quite nicely, but is this the best alpha choice? We could try an exhaustive search of different alpha values and comparing their performances, say with MSE, but this is very time consuming. Alternatively, we can draw on a unique connection between the exponential smoothing model and a model embedded in the sophisticated class of ARIMA models. ARIMA stands for Autoregressive Integrated Moving Average. And with that connection, we can find exactly the alpha that gives the lowest MSE. Thus, we'll call it the MSE optimal alpha. Many software can do this. JUMP in particular can do it. Excel unfortunately cannot find that alpha. To find the optimal alpha, we go to the time series platform, the same platform where we got the autocorrelation function. From the red arrow pull down, we can find smoothing model and then simple exponential smoothing. We'll give the option of unconstrained, which allows the software to have full latitude in the choice of alpha. Potentially, this could mean alpha is outside the bounds of 0 and 1. You could constrain it to 0 and 1, but I'm going to let it be unconstrained. Here's the output. We get a bunch of statistics, including AIC, Schwartz-Bayesian criterion, which is really BIC, and mean absolute percentage error, mean absolute error, which I called earlier as MAD, but I'm going to draw your attention to the optimal alpha reported here of 0.8659. I've presented two very basic smoothing methods, the moving average and the simple exponential smoothing model. They generally work fine for series that are stable around some mean level that remains horizontal. The challenges to these methods are when you have different behaviors like trending and seasonality. Consider here, for example, quarterly e-commerce retail sales as a percentage of total U.S. retail sales over a certain period of time, as you can see here on the slide. The series is clearly trending and seasonal. The moving average model cannot accommodate the seasonality, nor can the exponential smoothing method in their basic forms. Also, there's a subtle point here. At any given point in time, the moving average and the exponential smoothing method projects out a horizontal forecast. They're never accommodating the trending that might be in a series. They're always playing catch up. They're always one behind. So we're going to have to seek out alternatives. In their basic forms, moving average and exponential smoothing methods are best suited for time series that are meandering around some stable horizontal mean and not having a long-term trend. They also are not designed to model seasonality. There are adaptations to these methods to deal with trends and seasonalities, for example, double exponential smoothing, Winter's method. However, they're very complicated in my personal opinion, and it will start moving us away from our focus on regression. We're not going to cover these adaptations. We're going to use regression to deal with these different behaviors, and we'll find how well regression will do. Okay, that's the end of this lecture. Part 2 of time series will be the next lecture where, as I stated, we will show how regression can handle a variety of time series behaviors. Take care. See you next time.